Good morning, participants. I apologize for the delay in starting the program today. Okay, so now we are all set, and I think we can proceed. Okay. So we proceed again today on the day 2 session. Okay. So today I will. So yesterday we have gone through the introduction part of this deep learning, the first day, okay, and it's the second day today, and today it is our agenda to discuss about the deep feed-forward networks. So what is the deep feed-forward network? Okay, so first of all, I would like to tell you that feed-forward, what do you mean by feed-forward? A feed-forward network consists of the layers of neurons, and these layers of neurons are all connected, fully connected between the layers. Okay. So what I mean to say is,
I'm sorry, sir. Sorry for the interference.
No neurons
sir.
in the same layer are connected. Okay.
Sir,
Neurons
sorry for the
in
interference.
Layer,
Your PPT
connected.
is not visible, sir.
But every neuron in one layer is connected to the other neurons in the second layer. Okay. So likewise, so one neuron is connected to all the other neurons in the next layer, and similarly for all the neurons. So it is a fully connected network. Okay. So from between layer I and layer J, it is fully connected. Okay. Okay, I think now you can see the screen. Okay, so as I was talking, I'm mentioning that today, day 2, we go forward with the feed-forward layer, and in the feed-forward layer, as I told you, that you have layers of stacked layers of neurons. The first first layer being the input layer, and the last layer being the output layer. And the neurons between adjacent layers, they are connected, fully connected. Okay. So if there are, say for example, you take layer I and the adjacent layer J, then all neurons in I are connected to all other neurons in J. So when you take the connections between the neurons, it will be of the order I cross J. Okay. So that is what actually what you mean by fully connected feed-forward layer. Why we call it feed-forward is because there's no feedback. There's no connection from the from the next layer to the previous layer. There's always connection in the forward direction, and there's no connection in the backward direction. Okay. So if there is a connection from the next layer to the previous layer, then it is called a recurrent network. Okay. So that will come later. Okay. So first to start with, we start with the feed-forward layer. Okay. So the agenda for day 2 is biological neuron. Okay. And we have a short introduction to what is biological neuron, and then we go to the McCulloch neuron, perceptron. So all these 3 I have already talked about in the previous class, yesterday's class. But today we'll go a little deeper into the topics. Okay. Because the better you understand these topics, it will be easy for us to navigate to the higher concepts in this area of deep neural networks. So first we begin with the biological neuron. So the biological neuron is actually, you can see that here you have this structure, what I have shown here in the figure, that you have a cell body. Actually, this is a cell body. A neuron consists of a cell. A neuron is basically a cell. So it consists of a cell body. Okay, the cell body is called the soma, and that is the processing center of the neuron. Processing center of the neuron. So the cell body is connected throughout its neighbors. It's connected to all its neighbors using dendrite. You see a dendrite here. Okay, so dendrite are hair-like structures which connect to the cell body or the soma. So dendrites receive signals from other neurons, the neighboring ones, and pass on this information to the soma or the cell body. The junction between the dendrite and the soma occurs through something called a synapse. Okay, the point of connection between the adjacent neurons to the cell body. Okay, so the connection happens through dendrites, and the dendrite, when it pairs a junction with a soma, at that junction you find something called a synapse. So yesterday you remember that the synapse, what I was talking about, is actually a gap. There's a gap between the incoming dendrite and the cell body, and this gap is actually a place where neurotransmitters, a special type of chemicals, are released. Okay, and these neurotransmitters, they mediate the signal from one cell to another cell. Okay. So basically the brain is a electrochemical device. Okay, so it depends upon the electricity. Actually the information is processed in the form of electrical impulses, what you see in an encephalograph or what you see in an electrocardiogram, okay, ECG or EEG. But at the cell junction, these electrical processes are converted into chemical processes by means of neurotransmitters, and these neurotransmitters, I told you, make the junction either an inhibitory junction or an excitatory junction. And every neuron has one long arm. So this is a long arm, and this arm actually extends and then again actually it splits into multiple branches and connects to other neuron, the next neuron, through the dendrite. So here you see this neuron is connected to this neuron through this axon, and this axon finally branches out and one connection is made through the synapse at this point. And the output of the neuron, output of the biological neuron, propagates through this this axon. The axon is the medium that actually takes the signal output of a neuron to the next neuron. Okay, so it's basically a very simple unit. Okay, so basically brain is made up of millions of cells called neurons, and what is not important is the number of cells, but what is important is the number of connections between the cells. These connections are actually, they are malleable. Okay, they can be changed, okay, by learning, as I told you yesterday. So the amount of learning what we do changes the connection strength between the soma or the between the neurons, and that makes our information processing in the brain. Okay, so at the very basic level, at the very atomic level, no, sorry, not atomic level, the cellular level, the brain is a very simple device. But when millions of neurons and trillions of junctions make the brain such a complex device to understand. Okay, so a whole lot of consciousness, thoughts, brain processes, everything actually comes out of this simple operations. Okay, so that you should remember. And next we see how the brain works with a simple example of the act of visual perception. See how actually, so there are several regions in the brain. So we take one such region, that is the visual cortex. Okay, visual cortex is the region that is situated at the back of your head. At the back of your head, here you see that the back of the head, you see the visual cortex, and the visual cortex itself is not a single mass of cells, but it's again a layered structure. So you have the input from the retina. So retina is again a neuron. It's okay. Actually, eyes are actually what you call the extension of the brain. Okay, we take eyes as organs, but actually eyes are extension of the brain. So the retina, a special type of color sensitive, say light sensitive cells, they are connected through the LGN to the visual cortex, and at the visual cortex you have level V1, V2, then we have level V4, then we have this PIT, then AT, and finally the prefrontal cortex. Okay, so it goes on. Okay, so where at this and this motor control. Okay, so so actually it goes through a lot of layers. Okay, the input goes from the eyes to different layers and gets processed, and here you can see that some time delay is there, say 40 to say 60 milliseconds, or here 60 to some 70, 80 milliseconds. These are the time it takes for processing, and finally it goes to the prefrontal cortex where you make decision. Okay, so here actually what happens is the eyes that detect the images, they are assimilated in the brain. Okay, yesterday I told you that about the cat, which saw the brain cells of the cat, how they react to different orientations of the line. Okay, the brain does not, the neurons do not react to the entire picture. Some neurons react to the horizontal lines, some react to the vertical lines, some react to the diagonal ones. Likewise, different layers. So different layers perform different types of from low end processing to higher end processing. And finally, the entire image is assimilated in the brain. And then we understand, actually we do some understanding. Actually, we don't do some simply recognition. So understanding is much a complex task than recognition. And after the understanding is done, it goes to the motor control, and more from the motor control, you take appropriate action. Okay, through the spinal cord, moving your hand or moving your leg or something like that. Okay. So inputs and actuators. So inputs are sensory. Eyes are sensories, they sense, and the arms and legs, they are actuators. Okay. So everything is actually done in the brain, central brain. Okay. So this is what I want to tell you here is that all these things happen in the form of layers. Okay, that's very important. Okay, so from lower to higher. Say here you can see that you can see here. You see that you have, whenever you look at an image. Okay, so initially the first layer, it detects layer 1 detects the eyes, the nose, and the other simple things. Say it detects edges and the corners. Okay, when it goes to layer 2, maybe from V1 to V2, so the mouth is, say, assimilated. Say these two segments, they form the mouth, whereas these two segments, they form the nose, whereas these two circles, they form the eyes. So likewise, eyes, mouth, and nose, they are assimilated in layer 2. And when it goes to the higher layer, layer 3, these individual units, the eyes, mouth, and nose, now they together form the face. So the face is not detected directly as such, but faces are detected from low level features, that is your edges, corners. From edges and corners, you get your other higher level features like your nose, your eyes, and the mouth. And these nose, eyes, and mouth, again, these are form features, and then they form the complete face. So in this way, simple visual forms to high level objects are assimilated by the brain. So anyway, this is a very simple picture, what I have shown you, the very over simplified picture, how the brain works. Okay, but for understanding of our course, okay, like artificial neural networks and your convolutional deep learning, this is enough. This process is enough. Actually, brain is even much more complex than this, which actually not required for our case. Next, we get into the McCulloch-Pitts neuron. Okay, McCulloch-Pitts neuron. This I told you yesterday that McCulloch was a neuroscientist and Pitts was a logician. Both of them joined together and they created a very, very simplified model of our brain. Okay, or the neuron, not the brain, the simplified model of the neuron. So this figure, you remember that I shown you yesterday. So this is the cell body, okay, the soma, okay, which the biological neuron, I call this as the soma. And these are the dendrites, and through the dendrites, inputs are entered. Input x1, x2, xn are entered, and inputs are binary. Inputs are binary as far as McCulloch-Pitts is concerned. And this G is an aggregator. Aggregator means it simply makes a sum of it. For example, G of x is summation of I equal to 1 to n x of I. So it simply adds all G of all the x of i's. And it is possible that any one of the xi or many of the xi's, they are inhibitory. Because I told you, when I told you about the synapse can be excitatory or inhibitory. So if any one of the input x1, x2 up to xn, if any one of them is inhibitory, the output is always 0. Okay, so output is always 0, even when you have one single inhibitory input. Then say you just sum it, and based on the sum, this function f acts on the sum. Okay, so f of g of x, f acts on g of x and is 1 if g of x happens to be greater than some threshold. Okay, greater than some threshold, theta. Theta is a threshold, and theta is set by us. Okay, as far as McCulloch-Pitts neuron is concerned, theta is set by us. And here it is 0 if this you happen to be less than this g of x happens to be less than theta. Okay, this is one thing. Another thing I told you is, if any one of the inputs x1 to xn, if any one of the input or more than one input happens to be inhibitory input, then the output is always 0. So this is what you have to remember as far as the McCulloch-Pitts neuron is concerned. Okay. Next, I will get into the implementation of Boolean functions using this McCulloch-Pitts neuron. So this is I've taken 3 inputs x1, x2, x3. Okay, you take the first one. Okay, and here this is theta is a threshold. Okay, and output is 0 or 1. I always remember the same thing, that this white portion, semicircle portion, is the aggregator g of x, and this dark semicircle is a f of x. Okay. Yesterday somebody asked the doubt of what is f of x. F of x is a function of g of x. Okay, it is a function which acts on this sum of inputs, and theta is the threshold. Okay, output could be 0 or 1. So this is a McCulloch-Pitts unit, and here you see that I'm implementing an AND function. What is an AND function? When all inputs are 1. Okay, all inputs are 1, output is 1. Okay. So here you see that this arrow, when I put it this as arrow, it means these inputs are excitatory. They excite the neuron, excitatory inputs. But when I put a small 0, small bubble, you see at this end, then it is a inhibitory. It is an inhibitory neuron. Okay. So this is an inhibitory input, whereas this is an excitatory input. So when it comes to AND function, I have 3 inputs x1, x2, x3. Okay, all excitatory, and the output is 1. So when is the output 1? The output is 1 when all 3 inputs are 1. Okay, when all 3 inputs are 1, output is 1. So that is what actually the AND gate is. If any one of the input is 0, the output is 0. Yes or no? So what is the threshold? Now when I choose the threshold, I say the threshold is 3. Okay. Now only when x1, x2, x3, and x1, x2, x3 can take values 0 or 1 only. They can take binary values. When x1, x2, x3 all are 1, then I get a sum of 3, and my threshold is 3. So when my threshold is equal to or greater than, my sum is greater than or equal to the threshold, output is 1. Now in this case, output will be 1 only when x1, x2, x3 all are 1. Okay. If any one of the input becomes 0, then naturally what happens is the output will be 2 or 1 or 0. In that case, the sum will be, when any one of the input is 0, then the sum will be less than 3. In that case, my output will be always 0. So this is a simple implementation of an AND gate using a McCulloch-Pitts neuron. Similarly here, OR. So in OR, you know the function of OR. OR says if any one of the input is 1, then output is 1. Okay. If all inputs are 0, if all inputs are 0, output is 0. So in that case, what should be the same neuron, but when I change the threshold to 1. So what happens, you see now here, when any one of the input is 1, so it meets the requirement threshold and the output becomes 1. If all inputs are 0, in that case only output will be 0, because when all inputs are 0, the sum will be 0 and will be less than the threshold. Okay. In other case, if either one input or two input or all three inputs are 1, in that case it will be always greater than 1 and my output will be 1. So this is a simple OR function implemented using McCulloch-Pitts neuron. So similarly, this is a NOR function. So this is a NOT function. So NOT function, I just told you, I give an input, but this time this input is not a excitatory input, it is a inhibitory input. So when I told you, when you give an inhibitory input, the output is always 0. So here, when x1 is 1, so when x1 is 1, there's a bubble here, that means it is an inhibitory. Okay. So output actually, so it's a negative input. So automatically what happens, the output becomes 0. Here in this case, you take this case, there's a x1 and not x2. Okay, x1 and not x2. So you find that in x1 and not x2, x1 is an excitatory input, whereas x2 is an inhibitory input because it's not x2. Okay, not x2. Now, since x2 is actually always not, if x2 is 1, then output is 0. Always x2, if x2 is 1, output is 0. Okay, irrespective of what is x1. Okay, but if x2 is 0, in that case, if x1 is 1, output is 1. Okay, output is 1. So you have to remember this. Okay, so it all depends upon what kind of input you apply to the McCulloch-Pitts neuron. Okay, so similarly a NOR function, you know what's a function, what's a NOR function? So a NOR function is so what is the output of a NOR? So a negated, it's a negated OR. So in negated OR, what you do is both inputs are given as inhibitory input. Okay, when both inputs are 1, output is 0. When either input is 1, output is 0. When both inputs are 0, at that time only output is 1 because the threshold is 0. So when both inputs are 0, the threshold is also 0. So sum is 0, threshold is 0. So at that time output becomes 1. But for all other conditions, when any one of the input is 1, it is connected by a inhibitory edge. So in that case, what happens? The output always goes to 0. Okay, so this is what you have to remember. So here coming to the next neuron, and that is in case of say I was talking about say binary means I can represent in a 2D graph, but when it comes to a 3 input, so it is you need a 3D graph. Okay, now this is an OR function involving 3 inputs. Okay, so an OR function involving 3 inputs. So when I talk about 3 inputs, you see that there's a now there's a cube. Okay, so this cube is actually this corner of the cube is all inputs are 1. The opposite is all inputs are 0. Okay, and this is 0, 0, 1 likewise. So you can draw this every axis x1, x2, x3. I put them down in the form of axis, and what I've done is I have drawn a cube. And now what is that our job? Our job is to convert this McCulloch-Pitt into a OR gate. Okay, so when I put it into OR gate, now you see that any one of the input is 1, the output should be 1. So in that case, I set the threshold to 1. So if any one of the input is 1, it is equal to the threshold. So the output becomes 1. So in that case, what is this equation? x1 plus x2 plus x3 should be equal to 1. So that is the threshold. Okay, the x1 plus x2 plus x3 should be equal to 1. That's it. It should be greater than or equal to 1. That's all. So if it is equal to 1, it represents this plane. Okay, so you know that in 3 dimension, when you involve 3 axes, you get a plane. So this plane, the shaded triangle, what is shown here is the plane that has the equation x1 plus x2 plus x3 equal to 0, 1. Okay, anything above that plane, that is, whenever x1 plus x2 plus x3 is greater than theta, then things come above that plane. In that case, it is always 1. Output is always 1. When x1 plus x2 plus x3 is less than 1, in that case, we go beyond the plane. We go beyond the plane. That is behind the plane. That is less than the plane. And that case, the output is 0. Okay. So this is very a diagram to help you know what is R function. Okay. So here and this is the R function involving 2 inputs. Okay, 2 inputs. So in that case, I can represent it using a line. Okay. So anything above this line, that is x1 plus x2 equal to 1. Anything above that line, it is 1, and anything below this line, it is 0. Okay. So this is what you have to remember. So you take more example. So this is AND. Okay, AND. So you just see this. You just see the figure that this is the line. Okay, x1 plus x2 equal to 1. Okay, so this is a decision boundary, or I call this as a decision boundary in the case of R. And here the decision boundary for an AND gate, you see that it happens here, this line. That is x1 plus x2 should be equal to 2. Okay, because 2 inputs, if it is equal to 2, then it is 1, 1 comma 1. If it is greater than 2 also, it cannot be greater than 2 because x1 and x2 can take only binary values. So it will be 2. So in that case, output will be 1. So you see this is the line. So anything that is point on this line is only this point. So it is 1. Anything below this line, whether it is here or here or here, it is always 0. Okay. You cannot have any other values because our inputs are binary. Okay. So our inputs can be only this, or this. Okay. Right. This is for the AND. Now this is for the OR. Sorry, not OR. This is a tautology. Tautology means irrespective of what is the input, x1 or x2, output is always 1. Output is always 1 irrespective of the input. Whether input, both the input are 0 or both the input are 1, either one is 1, no problem. So for all cases, whatever be the value of x1 and x2, our output is always 1. In that case, this is called a tautology. So here you see that irrespective of what's the value of x1 and x2, even if an x1 and x2 is 0, the threshold is set to 0, so therefore the condition is true. So the output becomes 1. So you see this is a line. Okay, this is a line that represents the x1 plus x2 equal to 0. Okay, so that represents a tautology. Now you can see when I go through this figure, you see that it all depends. The classification, actually, it is something like a classification. Whether the output is 1 or 0 depends upon the decision boundary. Okay, so in this case, it's a line that's a decision boundary. Here it's a line, it's a decision boundary, and this is the line that is decision boundary. And where the line is actually placed, that matters. And that tells you whether it's an AND gate or an OR gate or a tautology. If the inputs are more than 2 or 3, say if the inputs are 3, then we get instead of a line, we get a plane. Okay, if inputs are more than 3, then we get a hyperplane. Okay, it becomes a hyperplane. We cannot visualize a cubical structure in a more than 3 dimensions. So in that case, we call it a hypercube and a hyperplane. Okay. So now what is that we have seen so far? We have seen in detail about how McCulloch-Pitts neuron works. Okay. But when I look at this, you see that what is the drawback of this McCulloch-Pitts? Okay, so even though it's very, in those days it was a breakthrough as far as this artificial neural network is concerned. But you see there are few disadvantages that these values are hand-coded. You see the value of theta is hand-coded. Okay. That is the threshold. We are giving the value of threshold as 3, 4 or something. We are just hand coding the threshold. And another thing is that we are giving only the inputs. x1, x2, x3, they are the inputs, binary inputs. They are either 0 or 1. They are not real. They are binary inputs. So in this case, effectively what happens is this McCulloch-Pitts neuron, you can design them But these neurons, they don't learn. They cannot learn. It's not possible for them to learn. Okay. So the learning component of this McCulloch bits is missing, and that's a limitation of McCulloch bits. Okay. So later people came up with more ideas about creating something called a better artificial neuron, that is the perceptron. Okay, it was done by Frank Rosenberg, and yesterday we discussed in the history. It was done in 1958. Okay. So in that case, what happened was, so a more general computational model than McCulloch bits neuron. The main differences being introduction of numerical weights. Say here you see there are weights here. So every input is actually associated with a weight. And I told you what is the rationale behind using a weight. The rationale behind using a weight is to emphasize something more on some inputs, some features you are emphasizing, some features you are suppressing. So that depends upon the value of the weight you assign for every feature or input. And another thing is that here x1, x2, x3, they can take on any values. They are it's not Boolean value, because in McCulloch bits you can x1, x2, x3 can be a Boolean value only, but here it's not a Boolean. It can be any value, any numerical value. So it is any real value. Okay. Then it was carefully refined further by Minsky and Paperet, and there also they have given the drawbacks of this perceptron that will come later. Okay. Today we'll see, but later we'll see. And here you see that here what we do in this case also we have a summing g that sums the input, but doesn't just sum the inputs, but it sums the weighted input. So it actually sums w1 x1 plus w2 x2 plus w. So w1 multiplied by x1, w2 multiplied by x2. So w1 x1 plus w2 x2 plus w3 x3, so on up to wn xn. So weighted sums are summed. So here you can see this equation. The equation is y is equal to 1 if summation I is equal to 1 to the n. I is equal to 1 to n. Summation of wi xi is greater than the threshold. Threshold is set here in this theta. Okay. If this weighted sum is greater than or equal to threshold, output is 1. Otherwise, output is 0. If the weighted sum is less than the threshold, output is 0. Okay. And just you can rewrite this equation. This equation you can rewrite. You can bring theta on this side. So what happens is it becomes summation I is equal to 1 to n wi into xi minus theta is greater than or equal to 0. Output is 1. Also learn this theta. Okay, I can also learn this theta. So here simply what I do is I attach another line I attach here, and that I call w0, because my w starts from 1 to n. I add one more line that I call it w0, to which I always make it 1. The input is always 1 for that w0, but w can be varied. And what is that w? W0? W0 is the theta. I told you, the threshold. The threshold itself can be learned. Okay, that's an advantage. In case of McCulloch bits, the threshold you cannot learn. The threshold has to be set by the programmer. Okay, but here in this case, the threshold can be learned. The threshold can be learned, and the input weights can also be learned. The algorithm can also learn to know which features are more important by adjusting the weights of w1, w2, wn. Okay, so now this equation I can write it like this: if w equal to 1, that is output is 1 if I is equal to 0, because I've added one more input, that is the bias. Generally we call it bias. Okay, so the x0 is always 1 and w0 is always minus theta. You see, I said w0 to minus theta, where theta is the threshold. Okay. So when so in this case, in this equation, you see, say what are the parameters that you can learn? The parameters I can learn are wi and minus theta. These are the two parameters that I can change. Okay, and by changing them, I can move the decision boundary. Okay, and So here W naught is the weight associated with the threshold, and the threshold is not a fixed quantity on the neuron, but it is again a learnable parameter. Okay, and in that case, now what happens is my W now varies from 0 to n. I is equal to 0 to n. W of I into xi should be greater than or equal to 0 if the output has to be 1. Otherwise, if summation I is equal to 0 to n, W of I into x of I is less than 0, in that case, output is 0. I think this is a clear representation of what I call a perceptron. Okay, so it's a much, you have to remember that inputs can be real values. They need not be Boolean values, they can be real values. And another thing you have to remember is that there's weight associated with every input. Okay, and the output again here is 0 or 1. Output is 0 or 1 only. Output can be either 0 or it can be 1. Output is not a real value. Okay, output is 0 or 1. Okay, now I go to the next thing. So here I tell you that this perceptron can learn, unlike your McCulloch bits, perceptron can learn, and this is the learning algorithm. Okay, so here actually what is the weighted sum I'm taking? Just you just consider this on the right side of the slide. You can see left side, you can see the algorithm. On the right side, you can see the explanation that the weights I can associate with a vector. Okay, the W0, W1, W2, Wn. It's a vector. Okay, you know what is a vector? Vector is actually array. Okay, and x is also an input in which x1 to xn are inputs, and 1 is the input associated with the theta minus theta. That is always 1. So 1 comma x1 comma x2 up to xn. So this is your input x, and this is your weight associated with every input. Now, what is the summation? Wi xi, summation of I is equal to 0 to n. W of xi is a dot product. Actually, in mathematics, if you learn linear algebra, when you are given two arrays or two vectors, if you take a dot product of the vectors, then it is called the output happens to be a scalar value. Dot product output happens to be a scalar value, and that can be represented in a matrix form like this. So in summation form, I can put it like this, but the same thing when I represent it in matrix form, it is W transpose X. X is a column vector, W transpose is a row vector. Okay, so generally vectors are column vectors, but when I put a superscript T, it becomes a row vector. So a row vector into a column vector is this. Just you can do it on a paper. You take a row vector and a column vector, you can see, you can multiply them, you get a scalar value. And that scalar value is the dot product, W dot X. Okay. So this you have to remember. And in this case, if this W dot X happens to be greater than 0, output is 1. If W transpose X happens to be less than 0, Y is 0. Okay, this you have to remember. And what is that learning algorithm does? I tell you. Learning algorithm has both positive labels and negative labels. Okay, so you know the data comes along with some positive samples and negative samples. Positive samples for which output is 1, and negative samples for which output is 0. Okay, so this is what any data set will contain, some input features followed by what is the desired output. Output can be either a negative sample or a positive sample. Say for example you pick up a negative sample. Say you pick up, so you just mix P union N, then randomly you choose input. Suppose if you choose a positive sample, then what you do is you add that weightage to X. You say W is equal to W plus X. That you have to do. W is equal to W plus X. If you happen to choose a negative sample, then you subtract W equal to W minus X. Okay. So this is actually what is that you have to do. Okay, so if it is a positive sample and sorry I forgot. Sorry, you take the AND condition I not explain. You take it if the X happens to be a positive sample. When does X is positive sample? When Y is equal to 1. When Y is equal to 1, X is a positive sample. And in that case, if this W transpose X happens to be less than 0, that means it's wrong. Okay. Your neuron is saying that W transpose X is less than 0, but the sample says that it is a positive sample. That means that's a mismatch. In that case, you have to update the weight. You have to update the weight in the positive direction. if your sample happens to be negative and the W transpose X happens to be greater than 0, again there is a conflict. Your output says that it's a positive sample, but your desired output is a negative sample. In that case, I have to subtract X from W. In that case, I have to decrease the value of W. So I adjust the value of W. So I'm adjusting the value of W based on my output. If my output is wrong, I'm increasing the value of W. If my output is if it's a positive sample and my output is wrong, I increase the value of W. If it's a negative sample and output is and if W transpose X is greater than 0, in that case I decrease the value of X. When I do this, what my algorithm does is it learns. Okay, so this is the perceptron learning algorithm. So this I will explain with an algorithm, with an example. So here you see that these 3 points, P1, P2, P3, they are positive samples, and N1, N2, N3, they are negative samples. Now I want a decision boundary which is somewhere like this. I want a decision boundary like this, so that positive samples come on this side and the negative samples come on the other side. So now take this figure 1. Now you take an arbitrary value of W. I take this arrow, the arrow without this arrow what I've shown here, the first figure is this is actually this one is a random weight, initial random weight, and after that in the second figure you see that I choose a positive sample. Okay, I choose a positive sample P1. Okay, and in that case you see that the angle between the positive sample and the negative sample is large. Okay, so this angle between the positive sample and the negative and the the positive sample and the arbitrary random weight is greater than 90. So when it's greater than 90, what happens is the value will this W transpose X will be less. Okay, positive sample, but W transpose X is less than 0. That is wrong. So what I should do? I should add X to W. In that case, what will happen is this vector will go little upward. See, this vector from this position has gone to this position. The second figure, you see that it has gone to the next position. So it means it has gone closer to P1. It has gone closer to P1. Now you see, take this angle. This angle is now less than 90. So of course, what happens is I have learned something from the first sample. Now next sample I take P2. Okay, P2 is the next positive sample. Again you see there's the angle between P2 and this updated value of W is still greater than 90. In that case W transpose X will be less than 0. So in that case again I have to update. In that case again update. Again what happens? The weight vector comes here. Okay, now you see the weight vector has adjusted with both P1 and P2. The angle between P1 and the weight vector and P2 and the weight vector is now less than 90. Okay, so now when less than cos of theta, when less than 90 is a positive number. Okay, so it is greater than 0. Now if you take say a negative sample, say for example at this point I take N1. Now you see the angle between N1 and this weight, updated weight, is very small, but actually it should be larger. The angle between positive samples and my weight vector should be less, but the angle between the weight vector and the negative sample should be greater. So in this case it is closer to the negative. So when I take the negative sample and I update the weight, that is I subtract the value of X, you see that this goes this way. Say it is here, but finally you see it goes here. Okay, you see here. So you see the value is also changed. Okay, the angle is also changed. Now you take another positive vector, say P3. Now you see the angle between this and P3 is large. Okay. Now when I do this again updation, now you see this angle becomes smaller and goes near P3. Now you see this is my weight vector. Okay. Now weight vector is this, and my decision boundary is always perpendicular to the weight vector. So my decision boundary will be always perpendicular to the weight vector. So now you see the decision boundary on this side. So when I take this decision boundary here on side, I have all the negative samples, and on side I have all the positive samples. So why I have been taking this angle cos, changing the angle is because that the cos theta alpha, which is W transpose X divided by norm of W divided by norm of X, is the similarity measure. We call it cosine similarity measure. We are using the cosine similarity measure to adjust the weight vector with the positive and negative samples. Okay, so this is basically what is your perceptron learning algorithm does. Okay, so it's so here you see both the disadvantages that are associated with our previous neuron, that is McCulloch-Pitts neuron, inability to learn, and another one only binary inputs. Okay, has been removed, and programmable learnable theta, learnable parameter theta, that has also been achieved here. Okay, so theta, that threshold, is again taken as a weight, as a bias. So bias and weights. So we are in a perceptron is a basic unit in a multi-layer neuron network or in a feed-forward network. Perceptron is the basic unit, and because of that, you will see that we are always interested in two parameters. Even when you talk about higher level, when you go to CNN or RNN or you go to deep neural networks, we are always interested in W. W is the weight matrix, and theta is the bias. Okay, we call it weight and the bias. Okay, so this is a simple illustration of this algorithm. I hope actually things are clear. Okay, now next is I'll talk about linearly separable Boolean functions. So a little bit on that. Then we'll get into some more complex Boolean functions. Sorry, arbitrary functions. So here you see that I've taken the case of OR, and inputs are given 0, 2 inputs and OR function. So this is a truth table of OR, and for this the output is 0. Okay, that means when output is 0, W transpose X should be less than 0. Then only the output is 0. When W transpose X is greater than or equal to 0, in that case output is 1. You see, output is 1. Okay, so this is a condition here. So W naught plus I is equal to 1 to 2, Wi Xi should be less than 0, for whereas all other three conditions Wi Xi should be greater than 0. Okay, W naught is your bias. Now in this case, from this tell me what do you infer from this first entry of the input. What do you infer? From this you infer that W naught plus W1 into 0 plus W2 into 0 should be less than 0, because now what happens when I multiply W1 W2 by 0, this terms gets vanished, so W naught will be less than 0. That's the thing you get. So my W naught should be less than 0. And the second, from the second truth table, second value of the truth table, when this input x1 is 1, so W naught plus W1 into 0 plus W2 into 1 should be greater than or equal to 0. In that case, W1 0 will go away. So W naught plus W2 should be greater than 0. In that case, I can just bring the W the other side. I can say that W2 should be greater than or equal to minus W naught. Okay, so just rearranging this equation. Similarly, when this is 1 and the other input is 0, so now you see W1, W naught plus W1, this gets eliminated, is greater than 0, greater than or equal to 0. In that case, I can say W1 should be greater than or equal to minus W naught. But when both inputs are 1, then I say W naught plus W1 plus W2 should be greater than 0. In that case, I can say that W1 plus W2 should be greater than or equal to minus W naught. So these are the 4 equations that you get. Okay. Now, can you satisfy this equation? Okay. Can you find a solution to this equation? Yes, of course, we can find a solution to this equation. Say I can put W naught as minus 1. Okay. And W1 as 1.1, W2 as 1.1. So W1, W2, both are 1.1. So 1.1 plus 1.1, what will happen? Will be 2.2 will be greater than minus W naught. Minus W naught is what? Minus 1. Minus of minus 1 will be 1. So 2.2 is greater than 1. And similarly, if I take any one of the input, W2 is of course greater, say 1.1 is of course greater than 1, and 1.1 is again greater than 1, and W0 is less than 0. So this is not the only solution. You can have many more solutions also. Okay, and the solution is shown here in this line. Okay, this graph, you can see the line, and that line is this W0 is -1 plus 1.1 into x1 plus 1.1 into x2 is equal to 0. So this represents the line, and that is your XOR. Okay, so not XOR, that's the OR gate. Okay, right. So you remember that this, in this way, W0, W1, W2, they can be learned. But in case of McCulloch bits, we assign the value to that threshold W theta. Okay. Now you take the example of XOR. Okay, so this is very important. In XOR case, you can see that again, by using the same logic, you say when both inputs are 0, output is 0. When both inputs are 1, output is 0. Okay, when either input is 1, output is 1. So here again, I can put the equations in this form, and I can put the values. When both inputs are 0, W0 should be less than 0. When W2 is 1, when this x2 is 1, in that case, W2 is greater than or equal to minus W0. In this, when x1 is 1, x2 is 0, in that case, W1 should be greater than or equal to minus W0. But when both are 1, W1 plus W2 should be less than minus W0. So is there any problem here? Do you see a problem here? The problem what we see here is W1 plus W2 should be less than W0, but whereas individually W1 and W should be greater than minus W0. Say according to equation 2 and 3, and W1 should be greater than minus W0, W2 should be greater than minus W0. Okay, but when you add W1, W2, naturally the sum will be greater than minus W0. But what we require? We require less than W0. So there is an inconsistency between these equations. So there is no solution to these equations. Okay, so that's why the problem of XOR is not linearly separable. That means what I want to say is I can never put a line here, straight line, and divide the space into two such a way that you have negative samples on one side and positive samples on other side. Or in other words, I can say you can never put a decision boundary which separates two samples, that is the positive sample and the negative sample. Okay, I think this is very important, because there's an inconsistency between the equations. That's the problem. Okay, now so what is that we have to do? Now we have to go for higher level. Now this cannot be done with a single perceptron. So that is what actually the drawback of the perceptron here at this point is. Okay, so you cannot do with a single layer perceptron. You have to go for multi-layer perceptron. Okay, so before we get into the multi-layer perceptron, there's one more small digression we can take. Say for example, you have two inputs, x1 and x2. Say how many Boolean functions can you have with two inputs? Say how many Boolean functions? Say, or suppose I say n inputs. If there are n inputs, how many Boolean functions can we have with n inputs? Like and, or, XOR, not, like that. How many functions can we have with n inputs? So just you can see that totally you can have 2 power n number of Boolean functions. This is the number of Boolean functions you can have. Now in this case, you put n equal to 2. When n equal to 2, because my inputs are only two inputs, so 2 power 2 is 4, and 2 power n, so it becomes 2 power 4, and 2 power 4 is 16. So totally I can have 16 number of Boolean functions. Okay, with two inputs I can have 16 number of Boolean functions. How many Boolean functions can I have with three inputs? So 2 power 3 is 8. 2 power 8 is how much? 2 power 8 is 256. So I can have 256 number of Boolean functions. Okay, so we take the simplest case where the number of inputs is 2. So now in this case I have totally how many? 16 number of Boolean functions, and that's we go here. Okay, and you can see that this input is 0 0 0 1 1 0 1 1. So these are the two inputs. So this is 4. Okay, and for each I can have different functions. Okay, so what is this function? F1 is a contradiction, meaning no matter what is the output, no matter what is the input, output is always 0. On the far end, no matter what is the input, output is always 1, tautology. So on one side you have contradiction, other side you have tautology. So F1 is contradiction, X16 is tautology. So these are two functions. These are Boolean functions. And what is this function? I think this you can recognize. F2 is OR function. Okay. What is similarly? What is F15? F15 is not F2. F15. Sorry. F2 is not OR. F2 is AND. F2 is AND function. Okay. F2 is AND. What is F15? NAND. F15 is NAND. So you see an AND function here and NAND function here. Similarly, you can say what is F8? F8 is OR. Okay, F8 is OR. What is this one? F9? NOR. Okay. What is F7? F7 is XOR. F7 is XOR. What is F10? F10 is not XOR. Okay, XOR, not XOR. Right. Now, among all these functions, 16 functions, how many functions are linearly separable and how many are not linearly separable? I already gave you an answer that this XOR is not linearly separable. XOR is not linearly separable. So, apart from XOR, what are the other functions that are not linearly separable? Yeah, right. So, the F10 is also not linearly separable. So, XOR and not XOR are not linearly separable, whereas all other functions are linearly separable. Okay. So, I can use a single cell, I can use a single perceptron to classify all other functions, except the XOR and the not XOR. Okay. So, this is a small digression into the topic of what you call Boolean functions. Okay. Right. Now, next, I think I can just go through some more slides. Okay, 2 or 3 slides are there. Now, another drawback with this Boolean function, with this perceptron is that it is a hard threshold. Okay, say, for example, this is theta. Even though I can learn theta, but that theta is actually a hard threshold. Okay, so that is when theta is equal to minus W0. At this point, you find there is a step function. It is a sharp discontinuity. So here it is continuous. Here it is 1. Here it is 0. But at this point, when theta is equal to minus W0, at this point, I have something called a steep discontinuity, okay, function. So this, whenever a function is discontinuous, you know that you cannot do differentiation, okay. And therefore, the learning is not so smooth, okay. It's not so smooth in case of perceptron learning, we are seeing. I either add X or either subtract X from W. That's actually it's not a smooth thing. Now, many people wanted to use a gradient descent approach. Yesterday I was mentioning that I can use a gradient descent approach which was used earlier for astronomy. Okay, the same thing can be used in neural networks for learning. So in that case, I want the function to be continuous. Okay. Only when a function is continuous, differentiable. So now I replace a step function with a sigmoid function or logistic function. This function is called a logistic function. That's the one shown in red. So here you see that this function is written as y is equal to 1 by 1 plus e power minus W0 plus W transpose X. So initially we were dealing only with W0 plus W transpose X. But we are now dealing with e power minus W0 plus W transpose X, and that is actually, you put in a function like this. Now you see that you can put the value of the entire thing, and if this entire thing in the bracket happens to be very large, in that case output will be 1. If it is very small, the output will be 0. If this thing in the bracket happens to be 0, e power 0 is 1. So 1 by 1 plus 1, that is 2, that is 0.5. So that's the middle part. Okay. When theta is equal to W0, at that point the value is half. Otherwise, the value saturates to 1, on this side the value saturates to 0. So this is actually a logistic function. So the output is not now 1 or 0. Now output is a smooth curve between 1 and 0. So it is something called a probability. Okay, like how much, say when I go to a movie, I watch a movie, if I say how much you like a movie, sometimes you may say it is not a good movie or not a bad, so it may not be a discrete decision like yes or no, but it may say, you may say, okay, it's good, 70% I can say it is good, but 30% I don't like it, something like that. So here I can give a degree of like or dislike to a classification. Say I want to classify cats and dogs. Say how much this animal looks like cat. I say it looks 90% similar to a cat, okay, or 90% similar to a dog. Okay. Now instead of saying yes or no, I give a degree of freedom to that. Okay. Right. So that's what actually you can replace this by this W transpose X. I can replace by Z, and this is what actually a perceptron theta looks like. And this is what a sigmoid neuron theta looks like. So it's smooth, continuous, and differentiable. Okay, so this is very things you have to keep in mind. And when I talk about the error surface, okay, so because in learning, what we are doing is we are always trying to adapt our weights based on the error between the input and the desired output. So error between the exact what we get, okay, error between the output and the desired output. So this is the error, and error can be represented as a plane, okay, surface. So this you see for different weights, W1, W2 are two different weights, and by adjusting the weights, I can reduce the error. And of course, I will choose something which is the lowest error. So this is something contour drawn here. Because of this step function. So here you see the contour is not a smooth surface, but whereas it is a step, something like that, the contour. So this is the lowest error and this is the highest error. So if you start from this point, then your algorithm will work in such a way that you have to come back to this point. But when I use a sigmoid neuron instead of a perceptron, instead of a step function, in that case my error surface becomes a smooth surface. Now here I can apply differentiation. Okay, but here I cannot apply differentiation. Okay, here I cannot find gradients. There's no gradient. Here the gradient is 0, but at this point the gradient is very sharp. It is very infinite. Okay, but here you see a smooth differentiation can be done, and I can have a very beautiful gradient. Okay, now here wherever you start, the red portion tells you the higher error rate, and the blue portion tells you the small error. Okay, the minima. So maxima, minima. So here I should always try to achieve the minima. Okay, I can start somewhere, and finally my algorithm should come to a place where the error is minima. Okay, now here you see this diagram, you can see that. So this happens to the gradient learning descent algorithm. So this can be applied to neural network. So here what is that we do is we update the weights. You can see the weight here, WT plus 1. T plus 1 here is the iteration number, I can say. W of t plus 1 is equal to W of t minus eta into delta Wt, where delta Wt is actually the differentiation of the loss function with respect to its weight. Del L is the loss function. Del L by del W is the delta Wt. Okay, and eta is the learning parameter. So my weights are updated. Wt plus 1 is equal to Wt minus eta times del Wt. Del Wt is this, and my bias of t is equal t plus 1 is equal to bias of time t minus eta into del Bt, and del Bt is del of b is again del of loss function to del of b. Okay, so this is what is called the gradient descent approach, where because I'm finding the partial derivatives, so I choose a smooth function. Now in this case, here on this side you can see how the error is actually moving. If you are starting somewhere here in this red region, then see how slowly by each iteration you are coming down the slope. You are always going down the slope. You are always going down the slope and opposite to the slope, and finally reaching to a place in your in the minimum error, and that represents the correct value of W naught and B. Okay, that represents W and B. Okay, so in the graph you can see it very clearly, and below you can see the algorithm. Okay, so this is a gradient descent algorithm. So this algorithm is going to be used extensively in our next case, that is our tomorrow we'll see in backpropagation. Okay, so this is the elementary thing. This is how weights are updated. Okay, in a gradient descent approach. Okay, now just last 2 minutes I'll take. Say, so far we have seen how a neural network either using perceptron can model a binary function, okay, a Boolean function. So we have seen how you can model a Boolean function, but here actually I told you can approximate any function, any arbitrary function I can approximate. For example, here you take this function, a blue line showing is a function, arbitrary function. We do not know what that function is, but that can be approximated by drawing some histograms like this. Okay, the figure below you find where delta x is a scale of x. Now, when I make delta x very, very small, that is I start differentiating. Okay, because I'm always differentiating, So when I'm differentiating, the delta x limit goes to 0. So when by differentiating, what happens is I'm able to adjust to better to that actual function. Here the fit is not, actually I'm not fitting it properly, but here when I reduce the interval, there is a delta x, now you see I'm able to fit it better, okay, like this. Now here you can see I can even make it even smaller so that I can approximate any arbitrary function to a given degree of precision. This delta x is your precision, it's the precision you are choosing. So to any arbitrary precision, I can approximate any arbitrary function using neural network. So how do you get this histograms? That histograms is actually, or I call it as tower. How do you make this tower? So these towers are made actually for different values of x. Say for example, for one value of x, a tower is made, another value, another tower is made. Finally, all these when things are added, you get this entire thing. So now you see that this is what actually we are going to do in our gradient descent, using gradient descent and backpropagation. We will be able to approximate, okay, any arbitrary function to a desired value or to a desired precision. So with this, I think I come to the end of today's program, saying that the important theorems that you have to keep in mind. Yesterday I just introduced them. Yesterday I introduced the UAT theorem, that is universal approximation theorem yesterday. Today there's one more theorem, says any Boolean function of n inputs can be represented exactly. You take the word exactly, okay. Any Boolean function of n inputs can be represented exactly by a network of perceptron containing one hidden layer. See that you just need one hidden layer and 2 power n perceptrons, and you need 2 power n perceptron and one output layer. So you just need a one output layer, one hidden layer. That hidden layer should have 2 power n perceptron, okay, where n is the number of inputs. If given this, any Boolean function can be approximated exactly. No, sorry, not approximated. Sorry, it is represented exactly. Okay, I don't need to do any approximation. So Boolean functions can be represented exactly by perceptron. But whereas if you come to any other continuous function, arbitrary continuous function, in that case, a multi-layer network of neurons or perceptron with a single hidden layer can be used to approximate. Here I can say use the word approximate any continuous function to any desired precision. Okay, so this is a theorem called UAT, that is the universal approximation theorem. So these two theorems are the building blocks of the basic neuron model when applied to artificial intelligence problem. Okay, so today I think I will wind up with this, and tomorrow what I will do is I will start with the multi-layer perceptron. Then tomorrow I will see how you can use regularizing techniques, okay, to make your learning more robust, okay, without overfitting. Okay, so that will be our topic tomorrow. So tomorrow we'll talk about a multi-layer perceptron. Then we'll go into feed-forward networks. Okay, then we'll see regularization procedures and how to make, overcome overfitting problems in learning. Okay, so today, thanks for your time, and so if you have any queries, we can go through.
Thank you, sir. Thank you for a wonderful presentation. Information for the participants, the link has been shared in the chat window.
So I'll just go through
the link is now accepting the responses. You can record your attendance over there.
Chat window and see if any.
The link is
If
online
anybody
now.
has
Now
any
you can record your
queries, you
attendance.
can unmute and ask also. That's also no problem.
I'm sorry, we cannot share the day one attendance because day one attendance has been finalized and it has been taken printout. No problem, you please record your attendance today and we will consider it. So make sure you record your attendance. Don't miss the today's attendance. And also tomorrow's timing, we will update in the WhatsApp group about tomorrow's class timing. We will update in the WhatsApp group. So please watch our WhatsApp group for the further updates.
I don't see any comment. I don't see any queries on the chat window. Okay, so I think we can wind up. Okay, so thanks a lot for joining this session. Tomorrow we will have the day 3 session. So tomorrow I think we can start at 11:30. Okay, but we will inform you over the WhatsApp group. Okay, thank you so much. Thank you.
Yeah, thank you, sir. Thank you so much. Participants, make sure you record your attendance. The link will be on live for next 10 minutes. So please record your attendance. And we will really appreciate, if you don't flood messages on the chat window. Definitely the attendance link will be shared at the end of the session. Please, from tomorrow onwards, please don't request for the link in the chat window because it will be disturbing other participants from listening to the SaaS session. So once again, I share the attendance link in the chat window. In case if you miss it, please record your attendance now. Yeah, and also some of the participants are requesting for the materials, PPTs and all. Definitely we will share all the materials on day 5. So all the 5 days PPTs will be shared to you. So no worries about your PPTs and all. Definitely we will share the materials. So in case if you have any doubts, you can raise your questions in a WhatsApp group or maybe in the chat window tomorrow. So group we have restricted, only admin can able to message it. In case if you want to ask any questions, you can send your questions to me and I will forward it to SR and SR will answer your questions. No feedback after each session. After each session, we will be having an attendance link. On day 5, we will be having feedback form. So make sure 5 days you are recording your attendance. On day 5, we will distribute your feedback form. So attendance is mandatory in order to generate the e-certificates. So make sure you record your attendance on time. So don't worry, in case if you miss yesterday's attendance, no problem. So make sure from today you're recording your attendance.